Hi, this is Dr. Harrington, and let's actually just do a numerical differentiation example. So recall, first, we have the derivative at some point x naught is going to be equal to, we have this as f of x naught plus h minus f of x naught divided by h, and again this is equal to if we put on our error term, and our error term was minus 1/2 of the derivative at psi times h. So don't forget that this term here, the error term, is what makes this particular piece equal. Okay, because normally it's an approximation. Alright, so let's go ahead and do an actual calculation. If I say, let's go ahead and let, and I'll just make one up, f of x is equal to the square root of x, and x naught is equal to 1.5. So for that, I'm going to have the derivative at 1.5 is going to be equal to f of 1.5 plus h minus f of 1.5 divided by h minus the error, 1/2 of the second derivative of psi times h. Okay, now this may seem a little ridiculous, and you rightfully so, if you start questioning what I'm doing. If we have f of x is equal to x to the 1/2, right, I have to compute the first derivative to find the second derivative, f prime of x, and that's going to be equal to 1/2 x to the negative 1/2, and then the second derivative is going to be equal to negative 1/4 of x, and then I subtract 1 from the exponent, and I'm going to have negative 3/2 there. Okay, now again, you may be saying, whoa, if we're trying to approximate the square root of 1.5, or we're supposed to, sorry, the derivative of f of x at 1.5, that's what we're approximating, then we have to know what it is in order to compute the error bound. And oddly enough, that is true in this case. So I'm going to go ahead and put this together and say that the error bound, from this, the error bound this part here, all right, I'm going to take the absolute value of negative 1/2, take the second derivative of psi, and then times h. And we already know that that's going to be equal to 1/8. I'll just write it out, h over 8. And then I'll just write this as psi to the 3/2. Okay. Now if I look at that, that's going to be less than or equal to, and let's find an error bound on this. So I'll have the absolute value of h, could be positive, could be negative, and I'll have 8, and let's see, I'm going to erase this here, it's too much. 3/2. Now notice if I go from 1.5 forwards, if I go one, so if I have, well, let me go back. So if I go from psi is going to go from 1.5 to 1.5 plus h, right? That's a decreasing function, so obviously that's just going to be 1.5. And again, I'm assuming h is positive, so that way I have the forward difference. So if I go ahead and type this in, my little handy dandy, and again, since h is positive, I can just be even better and just write h divided by 8 times 1.5 to the 3 halves. Awesome. Now, suppose h is equal to something like 0.01. Then, here's what we have. We have f prime of 1.5 is about something to the effect of f of 1.5 plus h minus f of 1.5 divided by h. And again, if I just put that into my handy dandy calculator with h being 1.5 or 0.01, I'm going to get something about 0.407501 ... And my error bound for that is going to be equal to 0.01 divided by 8 times 1.5 to the 3 halves, all right, which is about approximately 6.78 times 10 to the negative 4. Now you may wonder, why in the world would you even do all this process if you already know what the derivative is? Well, the answer is, if you are a physicist or a chemist or an engineer or someone working in natural sciences, you can actually figure out what this h should be to use the difference quotient to get your measurements within a certain amount. So for example, if you're collecting data, you need to know, well, should you collect your data every once a second, once half a second, maybe once every nanosecond or so? The question is, how much data should you collect? You don't want to collect too much because that becomes overwhelming. But you collect too little, then you have extra error. So the question is, how much and how often should you collect data?